Okay, so today our speaker, I think hopefully you guys can hear me through Vincent's mic. It sounds like you can. Today our speaker is Vincent Zaballa, and he's going to be talking to us today about managing computational experiments using something called Hydra, which is not the animal I have realized from reading the abstract. It's something else. So let's figure out what that entails. Go ahead and take it away.
And Vincent, do you want to?
Yeah, one post-disabled participant sharing.
Cool, great. You got it now.
All right. And there it is, okay. Cool. Everyone see my screen okay? Or, well, not yet. You guys see the screen? Oh no.
Can you do screen mirroring or?
Yes.
Yeah, okay.
Yes. All right.
Okay, but for some reason on Zoom, we're seeing this layout of it.
Yeah, we're just gonna do that layout.
Yeah,
for the Zoom
I've
people.
seen. Here, let me. One thing was trying to. What is your computer running something right now?
No, it's just getting.
It's Zoom. Zoom takes a lot of.
I just have a lot of tabs open.
You should stare at the entire desktop.
Should I restart my computer? Sorry, I'm not helping. I'll just stop.
Oh, it's presenter view.
Yeah, I'm about to fix it. Give me a second.
I think at one point we had 3 different views happening between there, and here. Okay, that looks
Alright.
good.
We got it.
I don't know where your mouse is, but.
I don't need it. All right, sweet. There it is. Okay. Yeah. Okay. Now we can start. Hi everyone. As Philly mentioned, I've been talking about Hydra. This is something, and an intro to Bayesian optimization. So Hydra is a tool that I found really helpful, and just wanted to share with everyone here that runs computational experiments to see if it can help them, and also take any questions you guys might have. And then also give a brief introduction to something that I really like and enjoy, which is Bayesian optimization. So yeah, let's get to it. So first of all, I think everyone here knows what is high performance computing, HPC. It's a place to run computational experiments in the cloud. Here at UCI, we have the HPC3, which lets all PIs and students have an account. And so I went through the process of setting up my labs last year, and it was a lot of fun, kind of. So, but it's great because you get like 100,000 minutes or something, or hours, 100,000 hours, I think, or you get a lot of hours, CPU hours. And so, yeah, so it's like if you need to run stuff and you need a lot of compute power, it's the place to go. Or if you need a GPU, let's say you want to train some neural network thing, then you can go do it there. So yeah, that's what HPC is. And just, case study about like my experience with it in the past year for what I do. So I run a lot of experiments, which is like an ensemble, I guess, in like machine learning terminology, and to figure out parameters fit data in optimal experimental designs. And like in a nutshell, it looks like this, where you have some prior information about what you're thinking about or studying, and then you want to perform inference to find, a posterior distribution of what you think. Like this is just really high level. I'm not going to go into the details unless someone wants me to. So once you find that posterior, you can then decide, are you satisfied or not, and then you can collect more data. And so that's the optimal experimental design part. And both of those are pretty computationally heavy. Like the inference part is computationally heavy. There's like neural networks there. There's also neural networks in the design part. So it's a lot. And so like I want to run an ensemble, which is a lot of these. And then that like totals out to about 50 to get like a sufficient sample size. And also sometimes like the computational tools you use aren't great and they'll just crash. So like, I usually get like 20 out of 50, which is like, cool, this will work, I guess. And then each experiment takes about like 8 to 10 hours. So like up to 500 hours in total. And so like, no one's got time to do this like if you try to do it on your like a collab or on your laptop, it would take forever. You could do something fancy, but it'd still take forever. So that's why you'd want to use the HPC, but you wouldn't want to actually do it. And also, like, you know, like my computer right now is fan. You can't hear it, but its fan is going pretty hard. So it would start. Your laptop would probably go up in flames if you tried to do this. So that's why you want to use the HPC. But when I first did it, I was pretty sloppy, and I'll kind of show you what I did. So when you manage these experiments, like any scientist, you want to keep track of everything you're doing. And like, this is how I did it, which is kind of a mess. And just like, what is this? So like, you can see I have like a software version up here, have some like parameters I'm interested in saving, like design rounds, all these things. It's just kind of ad hoc. It wasn't really great. You know, what day did I do this? And then, so like, yeah. You know, just ad hoc hyperparameter tracking, which isn't really great if I want to go back and look at what I did. You know, some of the file path is experiment dependent, like 2-step or 1-step. So it's like totally, and I didn't like keep track of like what it was. Yeah, customized. Like I was like, oh yeah, I'm just gonna change this in the middle of my experiment. So that's not great. And it came out to look something like this at the end. So that's like some arcane file name, which is like, this, you know, you need like a cipher to understand it, and it just wasn't great. And some of these things can be handled with argparse, which is like a Python tool. There's probably other things, and that's good. And I started to go down that direction. Like argparse has its own problems. You know, like it can blow pretty fast if you're trying to do certain things. This isn't actually the best way to do it, but I was trying to do like a sweep of like hyperparameters, but and like try to like automate it with the HPC, but this wasn't, yeah. Anyways, there are better ways, so that's not really great. So the conclusion I came to after I finished that paper was this sucks, and I need something better to manage experiments and to add like arguments and to keep track of these experimental settings. And so what I found was just to use this thing called Hydra, which uses a config.yaml file. And so this just makes everything easier. So let's say you have something called your app. This is just some stuff you have to import, but all you need to do is put this little decorator on whatever your function is. Like you need like one function or class that does everything. And then once you put this decorator on, you can put all of the hyperparameters, everything you care about in this config file. And then basically you can like put it into your function here. And it does like a lot of this tracking thing. So it can help you track your experiments. It can help you can do these command line overrides now. You can, you know, provide customizable interfaces and interpretable directory structures. So now instead of like that arcane thing, like it still is a lot, but at least it's words and not like random numbers. So, you know, it just gets a lot more, I guess, customizable, and you can automate things and just interpretable. And then also easy for colleagues to parse, because I actually did this because I had an undergrad who I said, yeah, just, you know, go and vim into the Python file, change these things. And she's like, I'm not going to do it. So yeah, now she can do it. And it's, yeah, so it's progress. Yeah, override commands on the command line. So this is how easy it is. You just say, you know, if you have that thing there, you can say like my app and then just change whatever you want. So root is now root instead of like Omri. The password is 1234 instead of secret. So it's really easy to customize this stuff.
Is that for like anything that's in your config file, or like those are automatically like converted into command line arguments, or do you have to specify that they can be overwritten using command line arguments some other way?
Oh, it's anything that's in your config file.
That's crazy.
Yeah, so that's the cool thing. Yeah, just anything in, if it's not in there, then I think you might be able to like add if there's like, but I don't know about that. But yeah, anything in the config file you can overwrite, which is nice. All right, so then, but how does it help you track experiments? Really briefly, in the output directory, you have a .hydra hidden directory that has the ingredients that you use for that experiment. So like one recent one that I did, April 29th, 7:32 in the morning. Wow. Yeah, this is the like that experiment for this C0. It has the config.yaml, which is what I used. And so you can see it up here nice and clean of like, oh, this is what I did that day. And I don't have to guess what this arcane file name is or like directory structure. It just makes, it's, I guess, uses more memory, but if you can manage that, then it's, you know, a pretty nice thing. So I'd rather trade off memory for interpretability. Yeah, and so what else can Hydra do? So that's kind of what I found like immediately useful, but there are also other things that I've been exploring recently. It has these things called launchers, which, so if you want to parallelize things, you can use job loops. So if you have a for loop and you want to run like 50 independently for one round, then it'll help you do that. You can launch stuff on Slurm with something called Slurm Submitted. So this is an interface with Slurm. So I've been meaning to look into this, but I haven't quite yet. But this is a nice tool that we can use probably here for HPC experiments to make things easier to submit to Slurm. There's also fancy distributed parallelization with Ray. So like imagine you want to like do in like parallel computations, but also like multiple rounds and like aggregate information, like take the average, then do something else, and then take the average. So that's what I've been playing with recently. I'll talk a little bit about. And it's just easy to add it. All you have to do is add this little line at the top of your config file, and it's ready to go. So it's pretty easy to like put this stuff together. It also has these things called sweepers. So sweepers is like for hyperparameter optimization. Like you want to find out what's the best configurations. One is Bayesian optimization. It's using this thing called AX, which I'll go into later. There's also Nevergrad for hyperparameters, and then Optuna. I kind of see Nevergrad and Optuna as similar, but I'm just going to talk about Nevergrad. So yeah, it has options. And just to go into like a little example, we're going to first talk about how to use Nevergrad hyperparameter optimization if you wanted to do this. So the example I'm going to give is, say you want to make a cell atlas with an autoencoder. So you have your genes by cells, and then you want to find some like bottleneck layer that is going to be your atlas that has some dimensionality. You want to check different architecture sizes, so different number of layers for encoder and decoder. And you also want to check hyperparameter settings, see which ones work best. It like quickly adds up to a lot of things, and like also in deep learning, like things aren't really like, it's a non-convex function that you're looking at, so you have a lot of local minima. So you want to try and find some global minima, so that kind of adds complexity just inherently there in your deep learning. And so Nevergrad is a useful solution that kind of like you can set some sweep and it'll do it for you, and come back to it later. There's some cool optimization techniques that it uses, like evolutionary algorithms. And so use this, come back to it, and you'll find like a ideal solution. But one thing that it may run out of memory depending on how long and how much, so you kind of need to keep track of that. I feel like whenever I run HPC experiments, I'm like, oh, it didn't finish because I didn't keep track of how much memory I had left. So that's a danger that I've run into.
Can I ask something about Nevergrad?
Yeah.
So like you're basically like doing a sweep of hyperparameters, and then you said it like can. So do you specify like all the parameters, or does it like start to figure out like what direction to go in the parameter space in a smart way? And like I guess at the end of each iteration, do you have to give it like a specific value that it's like looking to minimize or something like that?
Yeah, you'd have some like, you need to have some like minimization value. So like I guess for this autoencoder example, it'd be like the mean squared error. So you'd say like this is the one value that you want to minimize, but it could be multiple. You can make like a custom function, like mean squared error plus something else plus something else. So you need that, and then it's gradient free, so you don't need to have like a it doesn't need to be a differentiable function, so which most things aren't, so it's like if you have any gradient free function, like evolutionary algorithms will work with that. You change some parameters and keeps track of like where it's going. I think it has some other techniques. But those also have parameters. So the parameters on the parameters, but not as many. So you kind of set like a couple of parameters that you want to like for this evolutionary algorithm, for example, and then it will like help like run and get to an ideal, whatever your reward function is, like whether it's mean squared error or whatever. So,
interesting. Do you find that like how many parameters do you find yourself like sweeping at a time?
I'm just gonna add this little GIF. That's what it looks like. This is from their website, so I didn't make that GIF. Yeah, so it's like if you have multiple different like optimas, then it'll like converge to 2, for example. But yeah, for me, hyperparameters, I actually have kind of a lot that I've been meaning to look at. I just use good enough. Like I've got a lot, but I guess you want to specify like depending on how much time and like compute resource you have, you kind of want to like focus on like the main 3 or something. But And it's also if they're discrete, you know, or if they're like a continuous function, and it's like that kind of makes things different. I'll go more into that difference in the Bayesian optimization example after this. So that's never good. Any other questions about it before I move on? Cool. All right. So parallel processing, just I guess go back to it really briefly. JobLib. I haven't quite worked with it yet, but like I said, it's should work well if you have a lot of like parallel processes you want to use. Yeah, I haven't worked on it in Slurm, which might be like an issue. That's like there's like a little additional overhead of like figuring things out, because it's like you have to like specify each CPU and you have to make them talk to each other, and it's like I don't know how to do this, you know, out of the box. So you can figure it out, but there's probably something easy, and maybe Slurm Submitted does it, but I haven't quite done it. I've gotten Ray to work, and Ray is kind of interesting because you have like one main process that like talks to all the other ones. It works all right. Like you can do it, but you have to have like some custom Slurm script to do it, or batch script, and it's like, I don't know. It's also prone to errors, so sometimes it's like something is not communicating if it's on different nodes, and it's like I had no idea that was an issue. So yeah, I'm figuring these things out, but if anyone like wants to try these, I know I'm happy to help. But yeah, they ideally should work for parallel processing.
So I have a question for the like error prone nature of it. Is there like some sort of indication that you get when like a
Yeah.
process can't communicate across nodes, and that will maybe help it so that you can just like try rerunning those processes?
Yeah. That's the promise of Ray, because it's like it's supposed to be smart, and like if so it has like the main node, and then there's like, I guess what we call worker nodes. I don't know if that's the right terminology, but I'll go with it for now. So the main node, like, can detect if one node had lost connection or something, then it can like respawn one ideally. But they've kind of optimized it work for AWS and Google Cloud, like just all of those kind of things instead of Slurm, where you can kind of like orchestrate those things easier. With Slurm, I think you might be able to use it with the submit it, but yeah, it gives you messages in the logs, and I'm going through it right now, figuring out like, all right, this failed this way, and I need to figure this out, but I also need to submit this paper. So I'm gonna not use Ray right now, and I'll come back to it later. So that's where I am right now, is like, it's giving me, I've gotten it to kind of work, but then like, it gives like some error about like something not spawning correctly. And I'm like, oh. So yeah, it's built so that it should be able to like respawn a worker if it detects that. So yeah. Yeah, and let's talk about Bayesian optimization, which is what it has with Axe. So the Axe plugin, Bayesian optimization can be split up into two things. There's discrete setting, which you have multi-arm bandit optimization. So this is like you have different slot machines and you're trying to get rich. So you want to figure out which one has the best probability. Or, marketing emails, like you want to send out the best marketing email to get the most click-through rate. That's the example I'll go through here. So for marketing emails, let's say you start out with like, you have like 10 different emails and you want to see which one works best. You kind of want to like sample each one and see which one, but you also want to exploit the ones that work best, because you want to like get more clicks for your, your marketing. So there's like the trade-off is like explore these different options and also like exploit, the ones that work well already. So you can just see an example here where in the first round, the probability is, all distributed equally. You do an experiment and you kind of find out information. There it is. About, this one, it doesn't work well, and then the next round, this one doesn't, etc. And here's a good GIF that kind of shows what's going on. So you can think about like, you start like with priors that are very broad. You can see like they can all work, but then as you conduct experiments, you find out that some work better than others. And the ones that don't work well, you kind of like don't put a lot of thought into, and you can see like the ones that don't work, like they only give one experiment to, whereas the ones that do work well, it's like 3 or 2. So that's the explore and exploit trade-off I was talking about. So if you have discrete variables, this plugin will kind of just work. And so if you want to test, different layer sizes for your autoencoder or something, you can do that. So that's the bandit formulation, but it also works with continuous variables and with Bayesian optimization. So if you don't have a gradient, like I was talking to Sam about earlier, then you want to like kind of estimate what the function might be. So this is just an example figure of what Bayesian optimization looks like. And what you're seeing here is like for one parameter, that's a continuous variable. You have these evaluations of it, of like you try a certain value of it, and then it gives you a certain reward in a sense. And then you use a Gaussian process to find out like that's why you get this like these error bands. The Gaussian process is like basically a space of functions that you think might look like it, and then you kind of ensemble those together to get like average or the median here, and then you also get the variance. So use that Gaussian process, your posterior, what you think it could be, and use that with like an acquisition function. But again, Axe handles these things, so you don't need to know the details, which is nice. And then it kind of says, depending on how much you want to explore versus exploit, you'll then design the next experiment here, or next experiment to kind of go in that direction with the acquisition function. And in this example, you can see based off all these points, it thinks that right here has the most, chance of having high reward, and also there's a lot of variance there. So like with the acquisition function, it says this is like the most probably, this is the next best experiment we should do for this, what we think this is so far. But if you had it more geared toward variance, then it might go actually all the way to this other side where there might be more variance. But that's kind of something that you can play. Those are the parameters you might play with if you use like Bayesian optimization. So yeah, this stuff should ideally help people run experiments faster and get to what their answer better or faster and better. And yeah, that's Bayesian optimization, and actually my little presentation. So yeah, if you have any questions, let me know. Follow me on Twitter. Follow me on Twitter for like research updates, and I share papers. Like there's a cool paper I found recently about Bayesian experimental design and reinforcement learning. There's actually connections. So and other stuff that I think are cool. And this meme encapsulates me. I'll feel good saying experiment, but then I have to actually go feed cells. So yeah, that's it. Let me know for any questions, Zoom people, anyone else.
That's pretty cool. For the node-to-node communication issues, you're gonna want to talk to Matt Kirikoni.
Oh yeah.
He's
3 doors down.
What?
Not here
He's
right
3 doors
now.
down.
Yeah, he's 3 doors down. He's the HPC guy.
Nice.
He is you in 5 years, basically.
Oh yeah.
He's
Like-
you in 5 years. What did you just say?
Yeah. No, it's like you both came out very similar, like
yeah.
architectures and research areas and techniques.
Sweet. Yeah. I'll have to hit him up. Like, please help me.
Yeah, he's the guy for sure. He's also in Bayesian stuff.
Yeah, exactly, that's what I meant, like, yeah.
Should we just go grab?
Yeah, let's go. Like, Matt,
You can tell me, but
We will soon enough.
I guess the question I had was, what are you coding your neural nets in? Because you're doing neural nets, right?
Yeah. So I actually I do an ensemble of languages. So yeah.
you try like whatever PyTorch, TensorFlow, like
No,
all of the different.
Yeah, I try to do as little work as possible. So like, the thing I do is, since I do simulation-based inference or likelihood-free inference, somebody's built a library in PyTorch, so it's like, cool, this is a really easy API. Like I just need to do PyTorch stuff with that, and it's very simple. But then I needed to create my own normalizing flow, and I decided to experiment with JAX, and I was like, let's do this. And it's supposed to be faster. So like, I don't know, it's kind of faster, but like, I don't know if it's worth the overhead of like, my environments need to have multiple languages. But yeah, I use JAX and PyTorch for this in general. There's some weird issues of like switching, like Torch has its own like array things. You have to switch to like, yeah, there's some issues with that, but
I can imagine.
yeah, but I think with the JAX, it's like there's some functionality there that I wanted to have. So, but yeah.
So I would pick maybe one language, because you're gonna run into tons
Yeah.
of things going back and forth. The reason I bring that up is because there's like Ray Tune and things like this that are
Yeah.
supposed to, I haven't used them, but they're supposed to do hyperparameter optimization and keep track of things and stuff like that. Have you looked into Ray Tune at all?
Oh yeah, that's what Ray is. I guess Ray has that too.
Right.
Yeah, Hydra. Okay, one downside of Hydra is that you need to have these plugins. Like all these things work on their own, so you could do them on their own. But Hydra has a plugin that allows you to interface with it through Hydra. So sometimes there's like an issue of like you might be able to do it with RayTune by itself in your code. But if you try to do it through Hydra, then it's like a different process. So like, for example, I was trying to get Ray to work. Like getting Ray to work by itself would be little bit easier because the documentation is more clear, but like with Hydra, it was like, it's not as clear, and so there's some issues there. It's like, I don't know if it's a Hydra thing or if it's a Ray thing. So like, there's some issues if you want to use those plugins.
I mean, I'm hearing a compelling argument not to use Hydra. I'm not hearing a compelling.
Well, it's like if you
argument
want-
not to use Raytune.
Yeah, I think.
Do you know what I'm saying? Like, you're like, oh, Raytune seems to be a lot easier, the documentation.
Oh, no,
So why are you using Raytune?
Well, I guess it's like you don't have like all these other things like experiment tracking and like some other customizable things. And like I think it's just me, like I didn't have time to do it. But I think you can do it. Like I have example code from other people and it's like easy to use Nevergrad and submit it Slurm. And it's like, yeah, it just works with them. So it might be just putting some time to figure out like what are the little details with that. But yeah, I think Raytune, I haven't tried it. Maybe it's easier, but I think for both of those, the thing is getting to work on HPC and like for both robustly, because it's like the documentation's like, yeah, you could make it work on your local laptop, but the trick is like, putting it into like
Getting
the
into
cloud.
it, of
So
course.
it's like all these things look easy, but like Raytune looks easy and looks like it should be fine, but maybe when you put it on the cloud, it's still as hard. So I don't know yet, but that's all I can report back in like 6 months. So
I guess the last question I had quickly is, can you explain why your functions are not differentiable?
yeah, so it's not
Why
like
you need to use gradient free?
yeah, so like, yeah, we don't have a functional form. We just know the input and output. So we know if you input certain parameters, then we can get an output for a certain process. So like if you use an ensemble of models, then you're just averaging their outputs. And so you have all these different outputs, but like, I guess maybe you could differentiate through that, like an automatic differentiation thing.
You can.
But with an ensemble, I'm not sure, like,
You also can, because what you're doing with an ensemble, if it's an averaging function, then you can differentiate back through it.
yeah, but I think, okay, I think with the, so I think for me, like, I also have like different modules that do different things. So like the Bayesian optimization isn't like, I haven't thought about this. I guess that's why. So maybe you can, but like the Bayesian optimization, the Gaussian process, I don't know exactly how that would hook in with like the likelihood free inference. So if you can go all the way back, if you could differentiate through the likelihood free inference and like the Bayesian optimization, for example, then yeah, I guess you would. But I haven't thought about that. Really, it's just like,
You most probably can. There are ways, so even, I mean, I know very little about what you're doing, but so if you know about variational encoders, there's a whole thing where you have to like sample from the latent space, right?
yeah,
And technically, the way you sample is not differentiable, but there is a trick that they use called the reparameterization trick
yeah,
to make it differentiable.
yeah, I
Right?
think, yeah. Yeah, that's
So-
true, but I think for this, like, this is just high level, like, I guess I could figure that out, but in general, like, yeah, yeah, if you use Bayesian optimization, that's not a differentiable process itself. So that's I guess, okay, so
Why not?
that, because you're trying to estimate the mutual information, and that is something that doesn't have a closed form solution. So that is literally one part that is not differentiable. So that's why for me, I can't do it. So like first I need to calculate mutual information between data I've seen and like the parameters I'm trying to think about further. And that's something that doesn't have a closed form solution that I use the Bayesian optimization for in my program. So that's literally like, that doesn't have a continuous gradient. So once I figure that out, I'll design an experiment, go from there. And so I can't really, differentiate through that, maybe through all the other stuff, but yeah, for my thing, it's like design experiment, get posterior, and then find out best parameters. So it's like the whole thing is easier cast as like a gradient free process.
Okay, so we can, I have to run, we can continue this later. The only reason I bring that up is I think that typically, I mean, gradient optimization is like understood. Do you know what I'm saying? It's super
Yeah.
understood. It's very easy to do. It's very straightforward. This gradient free approach seems complicated, and it seems like, I don't know if this is true or not, but it seems like it'd take a lot more time.
Yeah, Gaussian process is O(n) squared, so it's like pretty computationally heavy.
Yeah.
But the alternative is there is no alternative for those gradient free. So I guess there's also evolutionary algorithms. That's an alternative. But you don't get uncertainty information, which is something that is a benefit of it. So if you have these Gaussian processes, you now have uncertainty measures, so you can like, if you want to get some explainability from it or try to like, look at it more. That's one benefit of Bayesian optimization. So I guess uncertainty and gradient free is why you'd want to use Bayesian optimization versus. And then even with like, if you use a gradient method, you still kind of have like, I guess you could do a Bayesian method with that, like a variational thing, but you don't really get uncertainty just with gradient based form. So, but yeah, there's easier ways. So that are also gradient based, that are Bayesian. So
Yeah, it was just a suggestion if you find that these things are taking super long. I mean, again, it sounds interesting, but in practice, I wonder if it's not worth it.
yeah, if I
You know what I'm saying?
Yeah, if I
So-
find something that's better, I am all for using it. So I'll look into that and see if I can differentiate through everything. So that would be awesome.
I got two questions.
Yeah.
So one might be stupid, it's like, how does Hydra differentiate from something more traditional like distributed computing? So I know something like packaging like Nimrod, where it's like, it's more about where you send the jobs in terms of counter space rather than like a Bayesian approach. Do you know how those approaches differ?
So it's more of a difference of where you send your experiments. Sorry, can you say it again?
So when I saw this talk, I thought of, there's this package back at home as in Australia called Nimrod, which is this distributing computing.
Oh yeah.
Yeah, so I think of that. So like, what are the differences and similarities between those two?
I
Because
think.
Nimrod was built for things that like with Bayesian, like it takes too long.
Oh, yeah. There might be some similarities. I think one of Hydra's thing is like it's not just for like optimization. It just has those plugins, and so like I said, those plugins have some. Their documentation is all right, and it's kind of like there's some hiccups when you're trying to implement it. But Hydra's kind of more for like experiment tracking and like configuration. Like,
Right.
so you can also use it for like databases and other things, or for like different models. If you want to like serve machine learning models, so it's kind of also like industry oriented in that way, not just experiment oriented. But yeah, it's not, I guess, it has capabilities for distributed computing, but that's not its main focus. It's more like just keeping track of all these things.
Got it.
Yeah. Yeah.
Second comment, which was, you kept mentioning the word ensemble. So like, are you familiar with Kevin Burridge's work?
Kevin,
Burridge, B-U-R-R-A-G. So he does a lot of ensemble method stuff
yeah.
with like, because you're talking about, your data is effectively similar to like ODEs. The model is ODEs, right? Because you care about signaling. Like
It's
not in BNP.
steady state that we use convex optimization to calculate.
Okay, so this guy does a lot of work in cardiac electrophysiology, so like action potential stuff,
Yeah.
but it sounds very similar to like what you, so maybe there.
Oh yeah. Would you mind sending me
Yeah, I can send you like
that'd be cool.
a link
Yeah.
or something, yeah, like maybe it was called.
Yeah. Ensembles are cool because it's like if you have like a point estimate, but you want like a distribution.
Yeah, exactly.
Yeah, you just get like distribution. So yeah.
You also care about this, I guess, in like epidemics forecast.
Yeah.
But the challenge is like the timing is easy to predict, but the magnitude is always off.
Oh yeah. Yeah, those are models that I guess are likelihood free.
Yeah,
I see a lot of papers like, yeah, epidemics, and so
yeah, exactly.
epidemiology. So yeah, yeah, you could use that there too, or ensemble methods would probably be helpful. So yeah, yeah, ensembles are cool. There's actually something cool that's called mixtures of experts. That's like it's like a new wave of it. So it's not just using the ensemble and getting like one, like you would use like the median or mean or something of the ensemble, but this expert is like you can think of it as like clever sampling of an ensemble. I'm not really giving a great description, but it's also another method to like I guess an alternative to ensemble that's shown good performance for some tasks. So mixture of experts. Sweet. Any other questions?
So I have a question. What are you using these methods to do?
Oh,
High
Yeah.
level.
yeah. So like, I want to do distributed, like for example, the array stuff. Like I want to be able to do like the ensemble thing. Right now, I'm just really doing like IID. So it's like an ensemble of everything very independent and ignorant of each other over different rounds. But ideally, I'd be able to do like an ensemble and then like collect the information for the first round and say, okay, let's use like either the top 5 or like median, instead of like having them all be like use half of them use some something dumb. and then go from there, and then kind of like try and see if that has better experiments. So that's kind of like distributional reinforcement learning, where it's like you have a distribution of actions or something and you want to sample like different ones. Right now I don't have I can't sample, like they're all like independent. I just see that there is a distribution that I can't like make a decision off of that. So that's the problem. Like that's what I want to do with Ray is like say, okay, I see a distribution and I want to actually do like choose like this part of the curve instead of like just having them keep going independently. So that's ideally, but if, I need to figure out how to get it to work on Slurm, and then I can do that. But yeah.
But what are the actual experiments that you're running? Like, is there
Oh.
like biological relevance?
Yeah, good point. So I work with bone morphogenic protein signaling, and so what they do is like, yeah, they like they gather experiments.
Big turn.
Yeah. So like you get like you can dose it with different BMP ligands, and then after 24 hours they have like a gene expression signal. They have a gene reporter that makes a protein, and you can put it in flow cytometry, and so you can get like a lot of cells of flow cytometry, and then they just take the median, but it might be good to take all of the values. And so that's a 24-hour time point, and so that's where the convex optimization when you math model, like that's the same thing. So now you want to say like, okay, this is the data, we want to fit the model of parameters. So that's how that works. And what I'm doing here is like experimental design. Like let's try and do this in a better way, like large scale. So like for that model, if you fully parameterize it, it's like up to like 500 parameters, and like they haven't gotten a good fit yet. And so like there's a couple issues with that, which is like, is it the right model for the system, or should it be something else? And so like a Bayesian approach is nice because you have these uncertainty, these uncertainty quantification that's like tells you whether or not it might be a good or bad model. And so ideally my methods would be like, okay, you apply this and you kind of automatically do that, and then don't really waste experiments. We don't have BMP ligands are expensive, so you don't really want to like throw the a huge budget at it and then not have good results. So you want to optimize for which experiments might get you the best results like fastest. And ideally we can do this with other areas of like, let's optimize for which experiments we think might be best by what information we have and like what information we think we have. So that's where this experimental design comes in. It's like, yeah, optimizing that. But right now I have like really toy baby problems, like because this is no one's really done it. So like I'm kind of taking the first steps, and so it's like, okay, first step is like, does this work? And then second step is, can we make it better and scale? So yeah, that's where my stuff comes in. One day, we'll have like a really cool, we'll solve biology with this hopefully, but it'll take a while.
Cool.
Yeah.
So I have to ask, do you know anything about demineralizing tissue? Which was that question from this morning in the workshop. Somebody asked, and we're like, we've never worked with bone before.
Oh yeah. Yeah, I was thinking you could just like, grind it up. I don't know.
You just grind up bone. Okay.
Yeah, collect it and then somehow process the cells out. Yeah, nope.
Nope. Okay, cool. I had to ask.
I don't actually gather the BMP.
Okay,
That's why I
okay.
understand BMP is a really good program.
Okay,
Yeah.
okay, fair enough.
BMP's everywhere. It's in
Exactly.
yeah.
Cool.
Right, Mike, and BMP's everywhere.
It's all over the place.
They're all
It
over.
really is.
Yeah.
Wait, I have a question. I don't know if it was asked. It might have been asked if I might have zoned out.
Oh, that's too late.
I heard like you were talking kind of a little bit about with the manual. I'm not sure. You were
Yeah.
talking about different languages. I would run all my things in Julia, but this seems like a Python program. Can I just use it with Python and call Julia from Python? Is that how I use it with Julia? Or can I actually use it with other languages?
That's a good question.
Yeah. I think it's Python only because it uses this like omega conf and diff config thing like that from the first. So
I imagine, I think I would use Python. Can I just call different languages from Python?
Yes.
Python will have that,
Yes.
so I can just do that.
You can do like a os.subprocess call.
Yeah.
Yeah.
what's
So
the other side?
if you could if you could like extract the variables that you've defined or the parameters that you've defined in Python and then pass them to Julia in that subprocess call, it would be messy, but you
It
could
would be
probably
gross.
do it.
Oh, yeah.
You just have to call each of the variables individually, which would
Yeah.
suck.
Maybe you have like a Python app that like defines everything, and then it talks with Hydra, and then the subprocess then ports that to Julia.
Mhm.
So it's like 1, 2, 3. That's how you do that.
Well, it might be worth it, because like honestly, I want to start doing more of this stuff, and one of the things that puts me off of it, it makes me just do it like locally or on other computers, is that I don't want to deal with all this, deal with all the organization. I'm not an organized human being.
That's what I just think for you, you have to be organized.
Yeah.
Yeah, no, that's a good point. I worked with Julia and I haven't thought about putting it into other languages, but yeah, if you, I don't know. Yeah, sub-processes. Yeah, it organizes your experiments so that you don't have to keep
It looks
track.
really nice.
Yeah. So,
Is Hydra free open source or?
yeah, I wouldn't talk about it.
Oh, yeah, no, it's totally different.
Should just $100. Yeah, yeah, cool. You use Julia?
Yeah.
Micah's here,
Someone-
we're all down here.
Yeah,
There's no
Julia,
good reason.
Matt left.
as to
Chris would
why I
be
use
proud.
it.
yeah, I
Just to
just,
be edgy.
yeah, I tried using it, but it was
Oh,
like,
Nargis just posted something called Hi Julia.
Oh,
Exactly,
there
that's a
it is.
wrap for Julia.
Oh, yeah,
Perfect.
I feel like I don't believe that those things work, like
Yeah,
our
like,
I
it's
don't
like-
believe that it
it's like-
works.
Fucking
They're
bullshit.
very scary.
Yeah, that's true. I'm scared of calling things with os.subprocess of Python, honestly, like. But yeah, I don't know, that's cool. Thank you, Nargis.
Yeah, I don't know if it's work or not. I try to sometimes call some R function from Python, but at the end I ended up not do that. But
ah,
I tried to flip as well, I couldn't like.
I ended up using the same function in the Python instead of calling the R function for Python. So
Yeah, high hopes then.
I don't know that's the same case for Julia or not, but
It's probably worse. Honestly.
maybe.
All right,
cool.
Thank you, Vincent.
yeah, thank you.
Thanks, guys. Yeah.